of them was also Royal Society London fellow. So like interacting with them and having idea of like what is exactly research and how they do, like, and you get some idea from them, and you're like sharing your experience or sharing your problems. So they suggested like if you are in engineering and then planning to shift into physics, then you should definitely convince to others that you are interested in physics. So they said like, yeah, work on research problem and research project, then you can also publish few research papers. So this is how like I started working. And then it was second year and I did intern at IIT Kharagpur, and yeah, it was like more of engineering project in cryogenic rocket engine. So yeah, there I did some CFD problem and studied some turbulence thing, and it was really nice, like how actually the PhD students work there and how they write their thesis and research paper kind of thing. I get to know there, and like yeah, it was first experience for me. And even after working for 3 to 4 months, there was like significant research work or like result which you can publish with any conference or any journal. So it was like first conference for me, like I did in second year itself. And you know, it was like ISRO conference, and there was only me who was from bachelor, and everyone was from like everyone were from like PhD or postdoc or professor or other scientist. So presenting your work in front of those kind of established professor and scientists. And fortunately, in during my presentation, the BrahMos CEO, like Mr. Misra was sitting in front of me, and it was really nice experience. And you are the only one, and like practically you must have heard like the self-motivation thing work really and really matter. Like this is how I got more motivated throughout the journey. Like practically you can learn from your past experience, and you can also get motivated from your past experience. So yeah, like then I started a small group in second year itself. Like I feel like research is all about collaboration, not about the competition. So when you have some small group such as like also citizen of science, the docent is trying to like to get together some similar kind of interested people and discuss some research ideas. So similarly, I did in my undergrad, like most of our colleges having societies or maybe like robotic society or SAE, but there is some there's no kind of society which are more focused on research work or research project kind of thing. So the option you have is the only working with professor or conducting research work with PhD student. And sometime in undergrad, like if you contact to some PhD guy, and then they will maybe there is high chance of like getting exploited with them. Like PhD students will give you some labor job, like building some or writing some code or writing some like formula or copying thing like Excel sheet, etc. So there's high chance, and during the curriculum, and sometimes professors are also busy, and yeah, conducting research with professor are really good, but maybe you can also do the independent research work. Maybe in later on we will discuss on that. So it was nice to form a small group and working on an independent research problem. And finally, we end up forming group as a organization. This is also like currently some of you might knowing that like Bosch.x. So our main vision is to provide a kind of research platform. So yeah, forming research group, and then it was third year and final year. So kind of, and I was working like 2-3 projects and working with professors. And I also during that I also did intern at IUCA, and then working with other nearby IIT professors. Like IIT Bombay was the nearest one, so you can also go there in weekend or whenever you can get some time. So working virtually, and then if you have some time weekend or other time like vacation, you can go and there discuss something. So this was all about the 4-year bachelor, and then yeah, it was time to apply for master or PhD. So it was like physics was the only option for me. Like Yeah, physics with there was some limitation. Like I had no time to prepare for GRE physics, so most of the physics courses in US require GRE physics. So like I had only option of Europe and other Australian countries. So yeah, I applied there, and most of the European and Australian university accepted me, and like yeah, it was nice. So I finally ended up doing my master's here in Sorbonne University, Paris, and right now I'm working at Kessler Browser Laboratory, and the project is about quantum fluid, and we are trying to generate a quantum fluid black hole on a tabletop experiment. So we'll be studying the black hole physics by applying the quantum fluid. Yeah, it was all about my till now journey, and like yeah, sorry for long. Thank you.
Well, that was very great, I guess. I mean, yeah, you took the motivation from the legends and then applied to yourself. And what's more important is that you started very early. So I guess that provided you a pathway that was very clear to you. Like you were searching for internships since first and second year, and then you were very clear about that. So yeah, that was great, Uncle, I guess. So
Yeah,
let's
the
move on.
basic we will discuss later on, but the one point is first thing is most important thing is you must know about your interest or passion. Basically, wherever you end up, like whenever, like I said, like, if you are interested in something and you're investing your time, definitely after some time you'll get some results. So basically, that's the key point. Yep.
So Bhavya, are you up?
Yes, Divyanshu. Hi.
Yeah, hi Bhavya.
So hello all. Yeah, hi. So hello all. I am Bhavya Bhatt. I did my bachelor's from IIT Mandi and graduated in 2020 with a computer science degree. Uh, so I got my interest in physics from a course we had, which was on mechanics of particles and waves. So this course had Lagrangian and Hamiltonian mechanics in classical and quantum mechanical settings, and the sheer elegance of these methods gave me motivation to learn it further. So I had by that time I had no interest in doing some research or even going into physics direction. It was purely out of the interest which I had after learning this course. So I self-studied for around 1 year, mainly quantum mechanics and about general relativity, because there was this very popular discussions about black holes, and I always wondered how these kind of quantities are expressed mathematically, or like how we really physicists really tend to learn about them. So the field was obviously general relativity. So I learned about general relativity in that 1 year, and then applied for internships at several places by writing mails to professors. This again, I had no intention to do like some long-term research. It was purely on because of my interest and wanted to learn what are the research side of the subject was. So I had my first research intern experience in my second year of bachelor's when I got an internship at TIFR under Professor Tejendra Pal Singh. So the project was based on quantum foundations, namely on measurement problems in quantum mechanics. So this was the type of project where you require very less basic prerequisites to appreciate the formalism on which the papers are based. Now, I think one thing in research is the ambiguity of which papers to read and which not to read and which are not relevant, and it becomes even more difficult if you are a student. So for this, always try to look for review papers, which sort of gives you a story-like description of that field, citing all the relevant papers and other literature, which has proved useful for researchers working full-time in that field. So I also started with this kind of review paper, which was written by my advisor and his collaborator himself. And I spent some days understanding the problem and discussed with students who were already working on the problem for some time before I had joined. So in research, I think discussions are very important because you cannot know everything, and this goes with all people. So discussion brings clarity and various other viewpoints which you previously had no idea about. Okay, and giving the problem several days in the middle of a discussion, something clicked, and I was able to map the problem mathematically to a much simpler problem of differential equations. Now, once I had made sure rest was just mathematical calculations which I was able to do quickly, as that was standard math taught in undergrad curriculum. Now this feeling of getting a solution to the problem is what you should try to get, and this comes naturally after you have spent several days or months or years, depending on the time scales of your research you are doing, trying to get your head around the problem and continuously increasing your intuition and picture about the problem. And then comes a point where you are able to derive very simple conclusions from this picture. And this is something which differs from person to person, I think. All good scientists will know the math and standard concepts, but it is this part of deriving conclusions based on the picture of problem which you have built that makes all the difference, I think. So after that, I latex my calculations, and then we also, there were a few of other students also. Those were VSRP students in TIFR. I was an student which got there through mail, so I just wrote mail to the professor and got selected. Those were VSRP students. So we all together wrote a paper and uh, describing this apparently new calculation. And then my internship got over with a published paper of my result in one of the German journals. So I think research is important because it gives you the realization of how incomplete our current standard textbook theories are, and where are the pockets in which these theories from where research field emerges. Okay, so there are some caveats in this standard theories which gives you opportunity to basically emerge these pockets into research field. Okay, and you don't need to have masters or PhD level knowledge to appreciate these pockets or caveats. Okay. um, so after that, I then did one research internship at IISER Pune in my fourth year on phenomenology of quark, gluon plasma, and other high energetic matter production in collider experiment. Uh, so this was the internship which required less of my physics skills and more of my computer science skills. Typically in data analysis and predictive modeling using machine learning and deep learning. Now, this is another advantage of doing research. I think you tend to pick up many sidekick skills which are different from your main research line, but you can make your journey smooth if you master them. And some of these skills are, I think, according to me, are like coding, data analysis, data visualization, simulation algorithms. And in today's research, you can also include deep learning and machine learning in your list. So that's another hot topic which is now currently being used in, especially in experimental parts of physics and even in theoretical work. So during this internship, I did not do any heavy theoretical work, which was supposedly my interest, but I compensated that by discussing a lot of theoretical physics with local students there. Now, IISER Pune had a wonderful curriculum, and they were exposed to courses like 3-level courses in quantum field theory, 2-level courses in general relativity, and so on. So all of them had a very strong foundations in these what are so called as sexy topics in physics. And so I really wanted to learn all of these topics, and so I discussed with them like how to go about learning them and so on and so forth. And again, discussions come to rescue when you are confused about something and you really can't know everything. So then these kind of discussions are the guiding poles in which basically tells you what to do and where you can proceed further. And as I was a self-studying student, didn't had much of background in these kind of courses, these discussions really helped me. Okay. Um, uh, Now, I would say that if you are doing on-site research, that means you are visiting a new institute, try to get a schedule of talks or colloquiums that may be happening in that time period of your stay. You can get this from local students there, and then try to attend every single of them. So I was fortunate enough to attend a talk by David Tong, which was visiting IISER Pune at that time, and it was related to dualities in physics. Now, many times these talks give you new directions to explore in your research and give you many new ideas which your research may or may not be using at that time. And this idea of duality is really stuck with me, and I can say that what all direction I have got in my theoretical physics journey, I am mostly focused on the topic of dualities, and this was the result of just attending one talk, which was very simulating. Okay, now here I want to quote a Feynman that being genius is not a mystery at all. You should have around 10 to 15 areas or problems which you think are interesting, and you have your own physical picture of these areas. And every time you encounter any new topic, you tend to apply your knowledge from these areas or topics, from these areas to that specific topic. Mostly you will fail, but for once you are successful, and then people say, how do you even thought of that? And I think these kind of colloquiums or talks give you that kind of opportunity to basically get new ideas for this kind of thing. After that, I completed my internship by writing some codes and submitting them to the department to build upon more sophisticated simulations and models on that by some local students there. Apart from these, in my final year, I did my major technical project in the field of theoretical deep learning and using some methods from statistical physics in the existing formalism. I explored many of the algorithms. I explored that many of the algorithms which were there in the papers had no open implementations available. Okay, and this was again a standard research process that you tend to first read about review papers which are written by some authors. You get to get a big bird's eye view of the research field, and then you try to read specific papers which are related to your kind of research. Okay, so I was doing that, and to my great surprise, I came to know that there were no open implementations available for the algorithms which were given in these papers. So what I did was I then wrote a Python library named PyGlo, Information Theory of Deep Learning, which was a kind of new, and then basically packaged it and published it on the online, and then later sent this library to the author of the theory, information theory of deep learning himself, and and he also appreciated that. So I think in research, what one can encounter is that you may encounter that something is missing, some pieces are missing, and then you tend to realize that. So don't stuck that someone may had already think about that and you just leave it. Okay, you pursue that, and to your great surprise, if you are succeeded in basically pulling off that task, it can be first time in that field. And the PyGlo was that kind of library. So previously no library had existed which basically discussed information theoretic algorithms in deep learning, and so PyGlo was the first kind of library. Apart from that, I also regularly do self-study and self-research, writing notes and so on, which and on topics which interest me. In self-study, I think one advantage is you don't know anything, and so you don't have bounds on what directions in which you can go. While self-studying, I think after 3-4 years of self-studying, I think try to read as many books as possible on a topic, and try to find pockets and caveats in the standard formalism, as I said. For example, you can learn about these caveats by Googling about them. Just Google them. Integrals. So don't worry about the of anyone who has not heard this word. But for example, if you are learning about path integrals, search about what other things are there in this kind of formalism. Then you will learn that there are path integrals called as coherent state path integrals, which are very important in many body theories. And then you are quickly drifted to fermionic path integrals, which are very important in many body theory as well as in quantum field theory. After learning some time about this kind of topics, you will tend to learn about constraint systems path integrals. And this naturally and directly drifts you to a whole research field of quantization of constraint systems, which is a research field in itself. So as you can observe that path integral is a topic which you encounter in standard textbooks, even in undergrad or at grad level. You tend to encounter this topic. And you can see how by self-studying and self-researching, trying to Google about them and trying to find caveats or some subtleties in the formalism, existing formalism, how you are drifted to a whole new research field itself about whatever all topic you started with. So I think in self-study, try to do that. Try to find caveats in the formalism and try to find how research field emerges from these kind of pockets which are left in standard theories. And I think research exploits these pockets only. So there are these pockets which are there in standard representation, and then researchers try to exploit these pockets, try to give new ideas about these pockets and so on. And I think that's research is. So that was my journey till now in doing research in general, and particularly learning about physics through self-study. Thank you.
Wow. Thanks, Bhavya. That was awesome. That was awesome. What I found peculiar is that we may never know when a particular course, internship, or talk changes our entire trajectory. But also, do not depend totally upon those things. Continue self-learning as much as possible. So yeah, I guess that's a very great point of source. So let's continue the meet. Vaibhav? Yeah, hi.
Okay, let me start. So, hello everyone. It's probably evening in India. I'm Vaibhav. Looking back, just to give a quick rundown of what I've done so far. After 12th, I also joined engineering. I don't know for what reason, but everybody's doing it. I did it too. Was very naive, and I guess. Did my engineering, was doing courses, and I think if I think what got me into physics, it would be that I guess I used to ask these very simple questions to mostly myself, and in the process of answering them, I think I was really excited. Like, for example, I remember everybody talks about circular orbits and gravity, and everybody does centripetal force equals gravitational force, these kind of things. But then you hear about that the orbits are actually elliptical, and I would ask myself, why no one talks about elliptical orbits at all, at least at that level. Go back and see how it happens, and that's great. That's something I found exciting. Or I remember in some physics engineering course, I remember being talked, I remember Pauli exclusion principle being talked about, and again, no one really taught the reasons why it works. Then I went back and tried to study and look for it myself. And again, it was very exciting. So, and basically these kind of things, these kind of basic questions, I think really motivated me to study physics. And I used to do it on my own because in my college, there was not much option to do electives outside my department. And there's just so many courses that I had to do for my own department. And yeah, that was the way I started reading about physics. And I did very simple physics. I used to do just undergraduate level physics, and I just wanted to build a core basic. And that was very enjoyable to me. Be it electromagnetism, classical mechanics, loved everything. And I think gradually, I guess, by my third or fourth year, I thought that, this seems fun and maybe this is what I should do. And clearly engineering was just something I was just passing the courses just to get through them. And so once I thought that physics is fun, and I thought I have some basics in hand, I thought I should get some research experience. And I remember what research experience I should get. I was very naive, so I had no idea about anything. But I just emailed a lot of professors, did not get replies mostly, got a lot of disappointment. And I remember finally I was doing an engineering required internship in Bhopal, and I figured, okay, maybe I'm in Bhopal. I said Bhopal could be an option. Emailed professors there, even went there. And I remember one experimental condensed matter physicist did agree to take me. I was like, okay, you can work on something for 2 months. And at that time, I was desperate. I was like, give me something. I want to do some physics research. Anything works. And that was good. Again, I got to do some experimental physics. Concepts that I only read was also good. I remember I did stuff like X-ray diffraction, Raman spectroscopy. It was all good. I think I did not get too many results in 2 months. I think maybe well, maybe I wasn't good enough or I didn't have much time. But that really, I think that pretty much cemented my belief that I do enjoy physics. I do enjoy just, that that whole concept of problem solving and sort of finding a pattern and finding a new effect. And I was like, okay, I'm ready to do a PhD. And I applied to, very naively every top university in the US. Got badly rejected. I had no physics courses, and yeah, that was a complete disaster. And I went back, and I was like, okay, what should I do? And I think the only clarity I had in mind is I do want a physics career. I had no idea in which field, but I definitely enjoyed physics. And so I was like, the only sure shot way is to do a master's, get some experience, learn what research is, get some research experience, and then try to make a career. And I think in hindsight, that was probably the best decision I made. I studied for JAM, did well, got into IIT Bombay, and basically, I think IIT Bombay completely changed my life. It was a great experience there, and I think I went in with a clean slate that I want to really explore physics at this place, whatever I can. And I think I honestly did that. I basically put my hands into every field that I could, given the time I had. I also concentrated well on courses. It was amazing. There were some really cool professors. And for research, I think I ended up putting my hand in everything. I did some experimental condensed matter. I did some theoretical condensed matter. I did a short project on astrophysics. I also ended up doing an internship in particle physics. And I was just exploring. I had no idea what I really liked. And at the end, in the PhD, I didn't do any of those things. But that was a great experience. And I think at that point, I was really focused on just learning. And I quickly realized that, if you want to build a career in physics, I think it's like a building. The base has to be really solid. And so I realized that your physics knowledge comes really handy. So I used to spend a lot of time, at least, studying quantum mechanics properly, studying classical mechanics properly, and all those things. And then I went on to advanced courses. So that really helped. And all the research experience, I felt that it was, I think I just enjoy physics, whatever field be. And honestly, I think for research experience, at least when you are at an institute, really the professors, what they're looking for is, high motivation and excitement. I always used to tell that, what I can ensure is that I'll definitely learn quickly, and I will spend my time. And, it's just some level of sincerity that you need. And I think most professors do agree to take you in your group once you show them that excitement and motivation and you do work hard at it. And so that went well. And I think, just interacting with professors, attending seminars at IIT, started giving me a clarity that I began to understand what kind of problems I enjoy. And it turns out that theoretical condensed matter was something that excited me the most. I remember being excited by problems like, high temperature superconductivity, things like that. And once I had that clarity in mind, I then applied to PhD in the US again. And this time I was not naive. I had some physics courses behind me. I was clear what kind of research problems I do want to solve. And I was not exactly clear as to what exact problem I wanted to solve, but at least I had given it a direction. That these are the kind of techniques I like. And it worked this time. And I did get admitted to a few places. And then I ended up going to Cornell, which was also good. I've been having a great time here. And then I had to decide which advisor to work for here. I ended up slightly changing my field again. And my current advisor, I remember going to his website and, attending one of his talks. And I think that was the field that finally sort of just, seduced me towards it. And so now it turns out I do theoretical ultra-cold quantum matter research. And just for a quick rundown or a 5-minute pitch for this field, I thought this field was really amazing. I'm really fascinated by this field. And the reason is that my one-line summary of this field is that it lets you study, interacting fermions and bosons in basically any setting you want. And that's what our world is made of, right? It's, for example, superconductivity, one thinks that it happens in a material, but a piece of material is messy. It might have defects, it might have dislocations, it has phonons or impurities or whatnot. And what ultra cold atoms let you do is that you have a clean lattice, a lattice made of lights. There's no defects, no phonons, nothing. And you just put some fermions in it and you ask, is there superconductivity? It is a very clean system. And you can ask these basic questions just removing all the bad stuff or all the stuff that's usually present in nature and just get to the core question. And I think that really excited me. Or, you can do funky stuff, neutron stars, no one knows its equation of state. But what turns out? That neutron star is just made of fermions. Again, what do? You put some fermions, you say, okay, I let them interact with this much interaction strength. What happens? And that's probably what's happening in the neutron star. So again, it just strips off all the complexity and lets you answer the basic question. Some people are building black holes from ultra-cold atoms. Again, it's simple. You don't need a real black hole. What you need is some sort of an event horizon. And once you do that, again, this field is just this playing ground that lets you do everything. And I think, that really excited me, that, this exploratory stuff that you can do with this field. And just, I thought this is the field that lets me do, pretty much any interesting physics I want. And I was definitely drawn into this field. I've been working in this field for 3 years. It's been great. I think, in PhD, you get to learn almost something new every single day. I think, as Bhavya mentioned, attending seminars, attending talks, that helps a lot. And, that sort of makes you think, what are the important questions that people are interested in? And that's another important thing about research, is that it's not about what you can solve, it's also about what other people care about, because you are inevitably part of a community, and, you have to think about what questions the community as a whole is interested in. So you get to learn those kind of things. And I guess looking back, I would say, and considering, I think most of the audience is probably undergrads, physics, engineering undergrads, I guess the most important thing I think would be, at least I thought in my journey so far, is that one shouldn't focus, I guess the main focus should be building that strong base, getting your physics concepts right. And that's, just the undergrad level physics. That should be solid. And I think, publishing papers, it's not like I published tons of papers or did research on my own. I think before the PhD level, I think what's more important is what skills can you develop? And one of the core skills is absolutely physics. And the other is, the other skills like computational skills or, experimental skills. I think if you focus on that, it's probably easier to get into a PhD. And once you get into a PhD, that is when you can actually focus on, producing new research. But certainly that wasn't my focus. And I think that helped me a lot. And that was it. That was my journey. Thank you for the opportunity.
Wow, that was great. So one thing that I noticed is that basic questions always lead the way. I mean, you repeatedly said about how you were searching about the basic things that makes you understand the different things. So that always motivated you to pursue things, isn't it, Vaibhav?
Oh, yeah, absolutely. Yeah, I really enjoyed just answering those basic questions. I think that was the gateway to get into physics.
Yeah, and also clearing out self-doubts and being clear about taking physics research as the career is the most important thing while starting. I mean, it always clears out the other things and doubts and various things, right?
Yeah.
Yeah. So, well, let's go ahead with our meet. So all the three panelists shared their journeys and surely motivated us today. So let's now move on to the particular questions regarding doing research and its technicalities. Now I will be showing some questions onto the screen. So hi, can you all see my screen and the question?
Yeah.
Or how to approach the right people, or what things should we keep in mind before getting to do a research? So, Ankul, can you answer that?
Yeah, sure. So before getting into the research, first I think being undergrad, we need to understand the urgency of research at our level. Like being undergrad, it's really important to put your hand into the research and understand the research methodology and the guidelines, proper guidelines you need to get into. And like if you read the history of Silicon Valley also, like uh, there was the professor and scientist who established first company, and then they started building $1 million companies. Like so, you can like just imagine like behind any startup, behind any business, behind any sustainable government, there's lots of research being done. So basically, this is what the need of research, and you should feel about it. And yeah, so how to do research at undergrad level? So basically, if I say, uh, if I classify the different ways of doing research, I can say there are mainly three types of doing research, like experimental, computational, and theoretical. So most of the time when we enter into college, like after completing our school, high secondary school, so our mind is like research is something about establishing Einstein equation or relativity something. Establishing E is equal to mc square is something about research. Or so this is what some how like you say in Hindi. So kind of this is the big picture in our mind is about research. So uh, research is something not exactly that. That is exact research, but the thing is they are kind of topic. They are kind of work you can do without even knowing the main like even after doing PhD, most of the you are not clear enough. So there's enough gap you can do also in undergrad. So as I was explaining, like experimental, theoretical, and computational. So when I was in second year in IIT Kharagpur, there were few PhD students who were just doing numerical stuffs, and their PhD is done with numerical calculation and computational work. So what I learned is like in BTech also, or even if you're doing BSc, you have enough concept building material or resources, YouTube video and books you have, and you have open source softwares, and you have computational resources. So basically, can you do that same thing in your some free time? Like, so you can learn some few basic steps about research. So basically, for that you need some theoretical background, basic concepts, and experimentally, yeah, like there's really huge difficulty getting the fund from government, and still in Indian, like I visited almost all old IITs attending conferences. So yeah, till now I had attended 7 international conferences. So in India, I visited almost old IITs. So I discussed with the PhD students, and they are also facing some fund issues and getting the experimental project. So this is what the difficulty right now even PhD students are facing. And when you are in undergrad or master level and you are like thinking of doing experimental project in physics like quantum optics stuff, that is really tough. So what is the option for you is the doing computational research. So the best option I found is like reproducing the result or just learning from the others research and like applying other method of computational work and generating data and then interpret it. So basically, most of time research is about 90% data collection and 10% or 20% is about interpreting it. So basically, data collecting means you collect the data from conducting experiment or running any numerical algorithm on any software or computational work. So basically, you collect the data and then interpret by your basic grasp on the like basic concept. So this is how exactly you can put your hand into research work. And the most important thing is like you must know the topic. Like uh, what I found is the best way to know your topic. Like if you are doing PhD, if you are doing physics course, physics bachelor course, then definitely you wanna be in physics. or either if you are doing engineering, or either if you are doing other natural science courses. So you know somehow the curriculum of your subject or curriculum of your field. So maybe the best option is to go through that, and whichever the points or whichever the topic you like most, then you can just put those separate and just search out them and just like have idea about those, and then you can go to some prominent scientist or professor who are working on that topic, and then go throughout their work and find out some good research papers, like 10 to 20 research paper, or like suppose if you choose some topic, then develop some ideology from back history to till now. So you'll get the idea how the real invention or real discovery got happened in present. So basically, this is how you develop the idea and problem statement, and then you start doing the literature survey. Literature survey you do, like you get to know about others, like what they did in the topic and how they approached and what are the available options you can choose, and likewise you end up framing a problem statement, and then you go to some solver approach. And solver approach means you're not just writing a problem statement of like black hole, some hypothetical question, like there is some popular science. So that those are not the exact problem statement. You need to understand like the solvable problem statement. You should be able to write that, and then approach from like available resources how you can solve those. So yeah, I think this is how you can do the research, maybe individual and also by approaching some professors under them. Thank you.
Yeah, that really cleared it up mainly. So, Bhavya, do you want to add something to it?
I think Ankul mostly covered how you can do research, but I want to add that if you want to quickly get your hands in research, then as I said that don't try to get into new kind of fields, but let's say if you are at undergrad level and you are studying subjects like classical mechanics or quantum mechanics, even in these kind of subjects you can do a lot of research, and there is a lot of interesting fields which extends to important questions. For example, in classical mechanics, many things that this is a closed field, and like it's just really have been confined to textbooks, and all of is known in classical mechanics. But if you do some quick googling or something, if you read Wikipedia pages, you will quickly know that there is this field again, as I said earlier, there is this field called as constrained Hamiltonian systems, which has many open-ended problems, and which is namely how you basically do classical to quantum and quantum to classical transitions. And this is these are all are open-ended interesting problems which you can motivate from as an elementary field as classical mechanics. So don't feel like in undergrad curriculum you will not find any, you will not be studying something which cannot drift you to research. Even classical mechanics can do that. And then in quantum mechanics you have all these questions which are based on quantum foundations. For example, measurement problem is one of those, which involves very interesting discussions about Schrodinger cats and entanglement and so on, which can easily be done at undergrad level. Then again in statistical mechanics you have a lot of problems in phase transitions and so on. So I think adding to Ankul what he said, if you want to do quick research, then just start by Googling and then try to see these pockets or caveats in the standard formalism and how these drift to research fields that themselves are quite interesting, so to speak. I think, yeah, that's it.
Okay. Bhavya, Vaibhav, do you have something to add on to?
Yeah, I'll just say that choosing or deciding what is a good area to research in, or what is a good project or what is a good problem, is highly non-trivial. I don't think I still have that skill because I've always done research with the professor, and I think, yeah, it's really hard to get good ideas. But what I would say is that, for example, yeah, if if you are working with a professor and if you're really just starting out, and if you're like me who has no idea what to do but wants to do something, I think it's you. Even if you're not fully prepared, you don't have to be fully prepared. It is okay. I think what you need is a lot of motivation and hard work, which is cliched but helps a lot. And every research problem, well, everybody who's doing research has a problem, has a well-defined problem that they want to solve, and which perhaps no one has solved. Otherwise, they would just cite it. And I think once you just dive into the problem, I think it helps just to go in with an open mind. Maybe you didn't know about this problem at all before it, and then you just jump into it. And I think you just learn what to do and how to do it in the process. And I think that experience of being in the process helps a lot. I remember in IIT, the first project I did with my eventual MSc thesis advisor, he just posed a very well posed. He just posed this problem to me that extra diffraction, you get peaks which are broadened, and that broadening is due to dislocations. What we're trying to figure out is how does that broadening relate to how much dislocation is there? It was a well-formed problem. I had no idea how to do it, and then he referred me to papers. I tried to learn it. It took some time. Just dove into the process, and I think that's the best way to learn how to do research. Just to dive into a problem.
So to summarize, doing research is to figure out problems and be persistent enough to understand and trying to solve it. Is it? I mean, that's what I understood.
Yeah, exactly.
So let's move on to the next question.